We'll keep going with this DOE 4, the screening design stuff, and then I'll hand your exams back. I've got to post the solutions on Blackboard still, but as you saw in the email, the average was like 68, 67, what was it? 67 something? 67 something. So a bit low. As far as my policy on curving, I don't curve individual exams, but I have often applied curves at the end of the class. And also, one thing that I will do in this class is allow you to take your final exam score and replace your lowest exam score with it. So if you had one bad exam, there is hope for that. So how I work that is I calculate the grades, just based on the syllabus, and apply any curve that I would do, and then get a grade that way. And then I redo it with having the final exam replace your lowest score, apply any curve, all that kind of stuff, and take the higher of the two sort of procedures for you. So that way, students that sort of do pretty well on all the exams get a fair deal compared to someone who maybe has a really horrible exam and replaces the final. But then it also gives you a chance, if you do have a really bad exam, to recover as long as you learn the stuff before the final. Question?
Consider the exams outliers and just
No, but good try. Any other questions on the exam? I'll hand those back here when we're getting the group problem. So, all right. So, and then again, if you got a low score on this exam, you probably want to go back and review things, because what we're doing now, as you can tell in screening designs and as we move forward, is all based on what we did in full factorials. So, all right, so let's look at this group problem. We're talking about screening designs. So here we have a screening design. This isn't in your text, sorry about that. It's a different text. And so it is, let's see, what did I tell you? I don't tell you much about it. So how many runs do we have? 16, good. So how many factors? Good, 5. So we would say it's a 2 to the 5 minus 1, right? 5 minus 1 is 4, 2 to the 4th is 16, so it's a 2 to the 5 minus 1 design, which means it's a half fractional factorial. How do we put those half fractional factorials together? Is we write the base design, which would be a full factorial in 4 factors, that's this, and then we have to add in our extra or added factors. So we have to do that by picking some design generator. 5 equals something. Generally some interaction between 1, 2, 3, 4, and so forth. And so what this is asking for, and since it's a half fractional factorial, we only have one design generator, and it's saying, what is that? And so all you got there is a columns of 1s and minus 1s. So why don't you take a minute now and see if you can figure out what the design generator was. Hint, if I were you, I would start with what design generator would you choose, what would be the best one, and see if that one works, and then go from there. Everyone okay with that? I know what we're trying to do? Okay. Go ahead and do that. I'll start handing stuff back here. Sean. Anybody come up with the design generator? Somebody did. Anyone else? Who's got a design generator? Okay, what'd you guys get? What'd you get, man? Right. Okay, so keep going on this. So the design generator that you would probably choose would be to confound x5 with the four-way interaction, right? Everyone agree that would probably be the best thing for a half fractional factorial? So that would mean, to check that, you'd say, well, is this, if I multiply those together, do I get that? And keep doing that, and you realize, yes, that is indeed what happened. So this column is also the 1, 2, 3, 4 interaction column. All right. So to get the resolution, we need the design generator, the defining relation. So what resolution is it? Good. So it's resolution 5, and the summary statement for resolution 5 is what? As concise as possible would be. Right. Main effects are confounded with higher order interactions. Two-way interactions are confounded with higher order stuff. And then we would just say the main effects and the two-way interactions are clear in those cases. So now let's think about if we're going to expand this in a computation table, what would it include? It would include the mean. It would include 1, 2, 3, 4, 5. And let's keep going. See if you can figure out what two-way interactions you'd have in there, three-way, and so forth. If you're wondering how many two-way actions are possible, we have 5 factors taken 2 at a time. Remember this? So we could come up with 10 two-way interactions. So just list them. questions? Got it, Scott? All right. Looks like a lot of people have them. Two interactions. We have 1, 2. You can just try to do them methodically. So those are the two interactions that have to do with factor 1. And then we can go 2, 3, 2, 4, 2, 5. We already have 1, 2 down. 3, 4, 3, 5. And then 4, 5. So that should be 10 of them. What about three-way interactions? Whoops. I could do this. 5 choose, 3. So we have 10 three-way interactions. But can I calculate those three-way interactions separately from what I've already calculated? No. So we've got 1 mean, 5 main effects, 10 two-way interactions. That's 16 things. We have 16 runs. So once I've calculated all these, and that, then everything else, every three interaction, say the 1, 2, 3, or the 1, 2, 4, 1, 2, 5, and so forth, those are just going to be confounded with the two-way interactions. And you could figure that out right there. So the 1, 2, 3 is going to be confounded with that 4, 5. Does that make sense? So when we set up this calculation table, we'll have these things as our column headings. So that's what this is getting at there. So we have the average, sometimes we call that I or mean. We have the 5 main effects. We have the 10 two-way interactions. And that's it. That's all we can calculate. Those 16 things and all the other effects are then confounded. Confounding happens in pairs. So sum product, and then here are the effects. Whoops. Our next job is just to figure out which effects are big, which effects are small, and so you can recognize, hey, that's pretty big, that looks pretty big. That one looks fairly large. I'm not sure of others, but we could try to do that by inspection. Doesn't work very well. And then we have the other option, probably the best option here, would be to make a half normal plot of all those effects and see which ones fall out in the straight line. So there's the half normal plot, and there it is. So in the group problem, I used to have people start doing that, but it got to be just too much to do in a group problem. So we have this line going through the origin. That is all of these effects we'd say are normally distributed, and the significant ones that are outliers are the x1, x5, and the 1, 5 interaction. So x1 and x5 seem to be doing something, and they are also interacting. So that's a pretty clean interpretation of the results. Resolution 5 is a pretty clean experiment, and so we would probably write that up in our model and use it. So we'll talk a little bit about what you do next in screening designs, and in this case we would probably have that simple model with x1, x5, and the 1, 5 interaction. Any questions on that? Okay, so the next thing we're going to do is back in full factorials, we had block designs in which we had variables that we wanted to try to remove their impact on our experiment, so to remove the noise. So in screening designs, we still have that concern. There still may be variables out there that we're not interested in making them factors or calculating what their effect is, but we want to try to we figure they're going to mess up our experiment. We want to try to get rid of them. So how do we do that in screening designs? It becomes a bit more complicated. We're going to treat them just like any other added factor. You know, we're going to say, all right, x, whatever it is, 6 is a blocking variable, and we're going to assign it to some interaction. But then we just have to keep in mind this is a blocking variable, which means whatever effect we calculate is just some block effect. It's not, we haven't really studied that variable. And then the blocking interactions we assume are 0. So we just have to keep those things in mind. The reasons for blocking are the same. So before, how do we do blocking in the full factorials is if we had 2 levels of a blocking variable, we did a full replicate of all the factors in this block and a full replicate of all the factors in that block. Do you remember that? That's a randomized complete blocking design. So each block contains the full factorial of all the factors. Okay? So that's great, but very often we can't do that. And so if you can't run, in block 1, if you can't run the whole full factorial, and in block 2 you can't do the same thing, how do you pick and choose which runs that you can do in each block? Does that make sense at all? So we're not running a whole set of replicates in each block. So that makes things quite a bit more complicated. So the solution then is this table in your notes, and let's kind of go through it. These are just different designs. I mean, you could, with what you know now, you could sit down there and hammer through, all right, here's my blocking variable, this is the best way to do that. But at this point, what we're going to do is just use this table and or Minitab to help us come up with the design, but we need to know what it's really doing. So we have to figure out how many factors do we have. And so we have 3 factors here, 4 there, and then 5 there. How many runs do we want to do? Okay, that's pretty self-explanatory. How many blocks do we need? And remember, the blocks are powers of 2. Block size just follows from the number of blocks, number of experiments. And then that appendix that I emailed out gives you, this is the table where you have the design, which says here are your factors, here's your blocking variables, run these high, low values for each of those coded variables. So then we have to think about what can we do, what can we estimate as far as interactions. And so, for example, this one's probably a good example to start. We can estimate these interactions. This is saying, all right, we have 4 factors. So let's just look at this one. We have 4 factors, and we're running it in 2 blocks. So we would need 1 blocking variable, right? So we'd write the 2 to the 4th design, the 16-run fractional factorial, and then we'd assign x5 equals the 1, 2, 3, 4 column, just like we did in that last example, except this time x5 is a blocking variable, not a factor. Right? So it's going to be a subtle difference in how we treat it because of that, but a lot of the mechanics of what we do are the same. So we're going to assign this blocking variable x5 to the 1, 2, 3, 4 interaction. So then, obviously, at the bottom of that column, that's what we're going to use to measure the block effect. And then these are the interaction terms. So it's given in terms of the variable. So this is, our defining relation is 1, 2, 3, 4, 5. So when we say the 1, 2, 3 interaction, that's the same as 4, 5, which 5 is our block. That's the interaction between the blocking variable, the 4 interaction. 1, 3, 4 is same as 2, 5. So that's x5, our blocking variable, interacting with x2. So do you see how the defining relation shows these things? It's not so clear that this 1, 2, 3 is the confounding of the 3-way interaction with a 2-way interaction, which is a blocking variable and factor interaction. Both those things we think are noise. Higher order interaction is noise. The interaction between a blocking variable and a factor is noise. So these are the effects we would use to get SE. Does everyone get that? Okay, that's how that works all the way down. I would say just note on these, this one in particular, that's a different animal. So those aren't blocking interactions. Those are, I ran out of it, not I, but I didn't make this table, but whoever designed this table said, boy, we ran out of degrees of freedom. The best we can do is try to use these two-way interactions to estimate the noise. That's not so great. I'd say both these designs are a bit sketchy in that we're trying to cram a lot of stuff into very few runs. So that guy's different. This guy's not so great. 1 degree of freedom for noise. That's not so good anyway. So you'd probably be putting half normal plots in these, and with only 8 runs, that's going to be a little bit tricky as well. So both those two designs up front there on the top, I'm just saying that's trying to get a lot out of just 8 runs. And so therefore, the interpretation is going to be pretty tough. But all these other ones are different there. Is everyone okay with this table? So we're going to use this table to do some homework and get a block design and use it. And so hopefully in your projects, which we should start having topics really close to being nailed down real soon. So if not, you probably want to try to get that done, say this weekend. Have a few project ideas developed enough where you can come talk to me, and I'll help you pick one that has the best chance of working, and we can tweak it a bit. So you want to do that again before the formal meeting. That only one group is scheduled so far. So, and remember, the deadline for that is coming up very quickly, and you don't want to be in the situation of trying to set up a meeting with me and my calendar's all full. Okay, so get that on the schedule. So make sure your groups are together and going on that. So the next thing you want to do, get a few ideas, flesh them out enough, or just informally come in and talk to me, and we'll figure out something that you can develop further for the project meeting. Okay, you don't want to come to the project meeting with an idea that I haven't seen and present it, and then we find a lot that's wrong with it, and then you haven't developed anything, and it's going to be, okay, that's not going to work, start over. Okay, then you're going to be real behind. Okay, is everyone okay with that, or at least understand it? Good. All right, so here's an example for blocking. And this is a very real thing why I bring up the project now, because in your project, it's the real world. One of the things that I want you to do is to figure out, okay, what variables should you be blocking out? And so, because blocking is a very good strategy, and we will try to incorporate it in your design. So let's look at this. We have an example. We're doing this ballistics test, and this isn't in your notes, but I have it here. Is we have 3 factors, and we're shooting stuff off, and we're measuring the speed of the projectile. So those are our 4 factors, and let's see if we can't run all 16 experiments on one day. So we got to split up our experiments over 2 days. And because of just the different conditions, perhaps wind, all those sorts of things, that we think that, all right, if we run some on day 1 and some on day 2, they might not be comparable. So let's try to adjust for that. Let's try to get that source out. Does everyone understand conceptually what we're trying to do? So we want to figure out, and again, we can't run all 16 runs in one day. So we need to divide up however many runs we can do across the different days. So in your notes, it mentions that we can run 8 runs in a day, and so we have 16 runs. So there's the base design, right? So there's the 2 to the 4th design is a 16 run, full factorial and all those factors. But then we had to add that blocking variables, so x5, and the choice that we've come up with many times already now is to say we're going to confound this blocking variable x5 with the 1, 2, 3, 4 interaction. Right? No surprises there. And if you look at this, these aren't listed as plus or minuses, but all right, when that's +1, that's day 2. When it's minus, it's day 1. Right? So you can think of that as plus, minus, minus, plus, so forth. So get that? So x5 equals the 1, 2, 3, 4 interaction. And so there, then we have results. These are those. That's the data. And then this is the results of the analysis, just given in a little different, a summary form. So it tells us here are all the effects, and here are all the t-statistics. We use some of those for error. Let's look at how we would do this in a spreadsheet, which I think is in your notes. It's on the next page of your notes. So that is this experiment. So we had 5 equals 1, or A equal, sorry, A, B, C. So E was our blocking variable, and equals A, B, C, D. So what I did is I wrote down the base design of 2 to the 4th, and I said A, B, C, D is E. You know, sometimes we would put that over here, which we did in the other example, but it's the same thing, just where it's placed. So there we have it. So then the defining relation is that. 16 variables, we can calculate 16 things. So we need to figure out what we can use for noise. Now, in a block design, we want to, the noise is going to be due to the blocking interactions, right? So the things that we think are not important would be three-way interactions and interactions between blocking variables and factors, even two-way ones of those, right? So let's see. In the confounding pattern, our candidates, these guys right here, would be good candidates for, you know, whatever effects down here are estimations of noise, right? But we got to remember, and it's always, or it's easy to forget this, is when you just look at this and say, oh, that's a three-way interaction, it's just noise. But remember, there's confounding that happens here, and we got to check that. It's not just ABC, it's ABC plus DE, right? Based on that defining relation. ABD would be what? CE. ACD, what? BE. And A. Confounding is happening in pairs, so these columns represent this three-way interaction plus this two-way interaction. So now, if I want to use these things as noise, do I think the ABC three-way interaction just reflects noise? Yes. The DE interaction, do I think that reflects just noise? Yes. Why? Yes. It's a two-way interaction, but why? Good. It's a blocking interaction. And same goes for that one and that one and that one. So all four of these represent things that are either higher order. They're higher order things confounded with blocking interactions. In both cases, I think they're noise. So we can take their effects and we can use those to get SE. Square them, add them all up, divide by how many? 4, and then take the square root. Okay, very good. So let's look at that. All right, so then this is what we just wrote down there. And that's the calculation of effects. And so there they are at the bottom of the column. We're going to square each of those to get 16.6 for SE squared. Square root of that is 4.08. And then we can calculate T values. Our T star, which is two-sided, 4 degrees of freedom. And then we just look to see those are all significant. None of these other ones. That one's real close. So again, in this class, when I ask you what's significant, you'll write down these 4. In the real world, you're going to not just ignore this because it just went below your hurdle value, which the alpha of 5% was completely arbitrary, right? So keep that in mind. You would look at this thing, this 2.67, this BC interaction, and say, that might be real. It's very close to call. All right. So we'd have all 4 main effects and perhaps an interaction. Did blocking seem to be important or not? Doesn't seem to be. Remember, that's the column that measures the block effect. Its t-value was 0.58. So we were worried about the different days messing with our results. Turns out it didn't really happen. So as I mentioned before, some people, when they see an insignificant block effect, would then say, okay, I'm going to take that and I'm going to throw that into the noise, and then I'm going to have 5 degrees of freedom and square that guy and add it up and update my estimation of SE. I'll get a smaller t-value because I have more degrees of freedom. This is common practice. I don't insist on it because it usually doesn't change things a whole lot. So if we did that, what's going to happen at SE, do you think? Is it going to go up or down? Think it's going to go up or down or not change much? I don't think it's going to change a whole lot. What about T star? Will it go up or down? All right. What? Oh, were you talking about SE? Oh, what did you get for SE? 3.8. 3.8. So it went down a bit. Not a whole lot, but it went down a bit. And then T star is going to go where? We're going to add 5 degrees of freedom, so that's going to decrease as well, right? So then, if we do that procedure, that guy might pop out to be significant, right? But again, keep in mind when you're doing this sort of thing, you're kind of splitting hairs. And it is perfectly valid to say, oh, that's close. Maybe we're going to take it forward. So I'm just trying to caution you on getting too locked into this very clear line of it's significant. If it's just barely over T star, it's significant. If it's barely under, it's insignificant. Right? There's a lot more to it than that. Okay, so then we would make a half normal plot, and we have those 4 main effects, and there's that 2-way interaction that's really, really close and suspiciously off the line. All right. Any questions? Just some tips then. I mentioned before, we generally don't, just rules of thumb, you don't spend more than 25% of your total budget on the screening design because stuff just might not happen the way you think. For example, you can't run all your runs, and you might come up with something that is pretty hard to interpret, and you might need to do some extra runs to chase down these confoundings, to break them apart. And that'll be sort of the next subject is, let's say you finish your screening design and the interpretation is tough. You've got lots of confoundings, and you go through our guiding principles of effect sparsity, remember that? And effect heredity, which effect heredity particular would be, I think we'll talk about it a little bit, so I won't. All right, so I knew I was talking about it soon. Effect sparsity, just a few of the things are significant. Then effect heredity, I don't know if I think we just touched on it, right? Maybe not even that. So that's saying when you have 2-way interactions, and let's see, so that's the official word-on-effect heredity. Let's say what that is. If you have interactions, let's say you have something that is factor E in a screening design turns out to be significant, and it's confounded with a two-way interaction there, another two-way interaction there, and a three-way interaction there. Let's make that up. Okay, so there are two, just these are interpretive guidelines for us. And the first one is saying, okay, I've got a significant effect. It's the sum of all these things happening, and I have to figure out what's happening. So my first choice would be to say, well, the lowest order of these things most of the time ends up being the one doing the work. So I would say, and it's tentative, these are tentative conclusions, that maybe it's factor E that's significant and not necessarily these two-way interactions or the three-way interaction. Does that make sense? So I would interpret this as, oh, this is a significant effect, probably the main effect. Now let's say you have a situation where you have a bunch of the same order. I'm making up these. I have no idea what the design generator defined relation would look like here. But let's say you have something like this, and the bottom of this column turns out to be significant. Now this first level doesn't help us, only that, well, the three-way interaction is probably not it. But now we have three of these two-way interactions, and we need to figure out, well, which is just one doing the work, is one significant and the other is not? And what this is saying is that usually a significant two-way interaction comes about from a significant main effect. So, for example, if factor A its main effect was huge, then we would probably, and C, D, and E weren't so big, then we would say, oh, that's probably the two-way interaction that we need to look at. Or we could say, if, say, both C and D are significant and none of the other ones are, we'd say, oh, that comes about from two significant main effects. So that's our first choice. Does everyone see that? That's what this is saying. This one is speaking to that example. So these are interpretations. They're not, they are fairly tenuous. So one of the things, especially if you have a lot of these that you're doing, then you probably ought to think very closely about, can I do some more runs? Can I add some more experiments? And maybe I can break up this interaction, where I can get this guy clear of those guys, right? Or I can pull out the factor E and eliminate its confounding with the other variables. So if we're good at picking some additional follow-up runs, we can do this sort of thing. So a couple pages down in your notes, I want to just talk about this one. Okay, that's in your notes. So if we're starting with the resolution 3 design, if you just have a couple main effects that turn out to be significant, we usually say, all right, run with that. You have, like that one example, we had X1, X5, and the 1-5 interaction. Okay, use that. That's a pretty good model. If, if we have a lot of main effects that are significant, then we say we probably need to do some additional runs to break up some of that confounding. So if you have 3, 4, 5 main effects that are significant, you think, wow, there's the chances of interactions are pretty good with all those important main effects. So I better check that by doing some additional runs. And it's a design that we are going to get to directly, or it's a way of getting additional runs. Okay, and so then the rest of it is, okay, if you have a bunch of two-factor interactions, are they easy to interpret or not? If they're not easy to interpret, which means this one, we keep going. If we can interpret it, we do it. So I'm going to show you an example of this part right here. So everyone's favorite non-food is non-dairy whipped topping. So it's an exciting career if you're working in the non-dairy whipped topping field, as you can see from here. So we're saying, what's going on? We're trying to make this stuff, and we have 7 variables that we're interested in, and the response is the whippability of it. So that sounds like a neat thing. And let me see if I can figure out if I've got the, I don't have the names of them. That's too bad. So, but anyway, they're going to run this design. They have 7 factors, right? So k equals 7. And they had these design generators. So that's 7 minus 4 design generators. That's going to be 8 runs, right? So that's a pretty saturated design. In 8 runs, we're going to estimate 7 main effects and a mean. So we're going to have lots of confounding. What resolution do you think that ought to be? 8 runs, we're going to calculate 7 main effects. Resolution 3, good. So we're going to have our main effects confounded with lots of two-way interactions. So this is, you probably recognize I did this in Minitab. So this is the abbreviated confounding pattern. Minitab calls it the alias structure, and it's just showing the 3-letter terms. There are lots more of them. So from this you can say, A, here are the main effects, and they're confounded with lots of two-way interactions, right? So A is confounded with those two-way interactions and so on. Has everyone got an idea of what the design looks like initially? So we run this thing. So again, it's a 2 to the 7 minus 4. It's resolution 3. It's how we write that thing down. We've got 8 runs. We can calculate a mean. We've got the 7 main effects, and we can calculate the effects at the bottom of the column. And there's lots of confounding happening. Keep in mind, this isn't just the effect of A. It's A plus the BD interaction, the CE interaction, the FG two-way interaction, lots of higher order stuff too. Okay, so now we look at these results. We say, boy, A seems to be doing something. B seems to be doing something. F looks pretty big. We should do a half normal plot and so forth and figure out if those things are significant. So Minitab does those for us. Notice the normal probability plot. When you have only 8 points, it's a little bit sketchy to draw a line. You've only got these 4. But it's saying A, B, and F were big, just like this one. One thing I want, and we have to interpret, we can't forget about the confounding. A is not just A, it's the BD, the CE, and the FG interaction as well. So what would your interpretation, so that those interpretive guidelines would say, what do you think would be happening in this case? What's important? What effects? We have 3 effects that are significant. This one, what would you assign this effect to? A, B, D, C, E, or F, G? A, right. Same with this one, B and F, right? That's the main effect. We'd probably think that's what's happening. So what we might do is, one way to proceed would be, okay, let's stop here, let's study these 3 further, right? But, and that's very often done. But when you have these 3 main effects, you think, boy, maybe we missed some two-way interact, maybe we missed something else because we had, you know, we had 3 main effects that were significant. So that could be a reason to say, before I just study these guys in a full factorial, let's do some more experimentation, break up this confounding pattern a little bit more, and see what we get. And so what I want you to do is look at this one right here. Something interesting happens with factor D. Factor D is really small. In the first 8 runs, it's doing nothing. Seems to be doing nothing. So then we want to run more runs. And so we want to break up confounding. And we're going to do that what's called a reflected design or a fold-over design. And so there are two ways that we can do this. We can depending on what we want to do. Okay, folded designs, really, we have two goals that we can do. One of them would be if we can do additional runs to break the main effects clear of everything. Right? So we do more runs, we remove A from this string of two interactions. We move B from that string. Okay? That's one way. The other way would be if we want to focus on a particular variable, we could break out B and all of its reactions and pull them clear. So the former is what's called folding on all factors. That takes the main effects and makes them clear. The other one, the latter, would be folding on one factor, in which, as my example was B, that would make the main effect of B clear, and all interactions with B, it pulls them out of any confounding. So you have to look at your data and say, okay, where do I think I'm going with this? What do I want to pull clear? Most of the time, you probably want to break out the main effects. So how do we do that? How do we do additional runs to pull that guy out of there, and this guy out, and that one, and same with C and D and so forth? It's a pretty easy thing to pull off. What you end up doing is you take your first 8 runs, and you look at your runs, and then you just switch all the signs. So our first 8 run, it would have been -1, +1, -1, +1. We just switch all the signs and run it again. That's what's called folding on all factors. And what it ends up doing is it breaks all the main effects from the two interactions. So we switch all the signs, we run another 8 experiments, and we get, okay, factor A, it was doing about that before. Factor B was doing about that before. F also behaves similar in the following up runs, but this is the one I was asking you to watch. Before, D was doing nothing. Its effect was 4. And now, when we just switched all the signs, its effect is -63. Ooh, and I'm sorry to do this to you, but that's going to be our Friday cliffhanger for today. What happened with factor D? Does it make sense? Okay, so that'll keep you coming back Monday.